I'm not going to do an integration by parts problem that I think is just a fun problem to see because one, it's kind of the example a lot of people use, and it's sometimes even a trick problem that's given on a really hard math exam, or if you go to calculus competitions like I used to in high school. Not to make myself too. I was actually not that geeky as a high school student, but I have to admit I was a mathlete. But anyway, this is just a fun integration by parts problems because you actually never have to evaluate kind of the final integral. So let's say we want to take the integral. It's a bit of a classic. You'll see this. I wouldn't be surprised if your math teacher does the same problem for you just to show you integration by parts. Let's take the integral of e to the x. You probably never heard of someone call a math problem a classic, but hopefully I will instill in you this love for mathematics, and you will also consider this to be a classic problem. E to the x times cosine of x. I think you might already see where I'm going with this, right? Because these are both fun functions, because e to the x, you can take the derivative, you can take the antiderivative, and it still stays e to the x. Cosine of x, you take the derivative, you go to minus sine of x, then you take the derivative again, then you get to minus cosine of x, then you take the derivative again, then you get plus sine of x, right? So it's like the cycle, and the same thing happens when you take the antiderivative. It's not as cool as e to the x. It doesn't stay exactly the same, but it kind of cycles. Every time you take a antiderivative, if you take two antiderivatives, you get back to the negative of itself, and if you take two derivatives, you get back to the negative of itself. So it's also a pretty cool function, and I think you can start to see how integration by parts might be cool here. So whenever I do integration by parts, I always like to assume that this is the g prime of x, that e to the x is g prime of x, right? Because e to the x literally doesn't change. Although we could do this problem the other way. Actually, maybe I'll experiment doing it the other way. But let's assume this is g prime of x, and let's assume that this is f of x. Right? This is g prime. So this is the derivative. So integration by parts says we take the original functions, g of x and f of x. So g of x, if this is g prime of x, what's g of x? What's the antiderivative of e to the x? Right, it's just e to the x. I'm going to switch colors. I don't like this blue. So this is g of x, right? I actually took the antiderivative of it, but it's the same exact thing. And then times f of x. And then I want to subtract the integral, the indefinite integral, of f prime of x. Well, g of x, right? G of x. This is the same as this, which are both the antiderivative of this, although they're all the same. So this is g prime of x. This is g of x, sorry. And then I want to take the derivative of f of x, f prime of x. So what's the derivative of cosine of x? It's minus sine of x. So sine of x dx, and it's minus sine of x, right? So I could put the minus here, that'll make it look messy. I could put the minus here, that'll make it messy. Or I could just say put a minus here, make these minuses cancel out, and I get a plus here. So I get the integral of e to the x cosine of x dx is equal to e to the x cosine of x plus the integral of e to the x sine of x dx, right? Hopefully I haven't confused you too much. I should actually probably do some integration by parts problems without e to the x, because it's very hard to keep track of what I've done here. This is the antiderivative. This is the antiderivative, and this is also the antiderivative. This is g prime of x. This is g of x. This is g of x. So once again, we are not clear whether we've made any progress. We've gone from e to the x cosine of x to e to the x sine of x. Let's take integration by parts again. See what happens. So I'm just going to write on the right side of the equal sign because this might get a little long. So this equals, so I'm just going to write this first part, e to the x cosine of x plus, and now let's do integration by parts again. So once again, now in this round of integration by parts, for this round of integration by parts, this was g of x. But now, for this round, I'm going to assume it's g prime of x. Which doesn't really make a difference because when I take the antiderivative of it to g of x, it stays the same. And then I'm going to assume that this is f of x. Right? So integration by parts tells us we take f of x times g of x. Right? So I take this function and the antiderivative of this function. Well, the antiderivative of this function is once again just e to the x, and then f times that function unchanged, right? Times sine of x. And then from that, I subtract the integral of the antiderivative of this, right? Or I take of g of x, which is e to the x. And then the derivative of f of x, right? F prime of x. What's the derivative of sine of x? What's cosine of x? Cosine of x, d of x. Let's see if we're getting anywhere. It seems like I'm just keep adding terms and making it more and more complicated. So in order to see if we're getting anywhere, let me just rewrite the whole thing and maybe get rid of these parentheses because it's just a plus, so we can actually get rid of the parentheses. So I have, let me use, no, I want a new color. Okay. So this is the original problem. E to the x cosine of x dx equals, and now let me switch back to this color. It equals e to the x cosine of x. And then I could just, this parentheses doesn't matter, right? Because I'm just adding everything in the parentheses. E to the x cosine of x plus e to the x sine of x minus e to the x cosine of x dx. Now you might think that I arbitrarily switched colors here, but right when I rewrote this. But if you look, you might see why I actually did switch colors here. See anything interesting? Exactly. This is the same thing as this, just a minus, right? So we're going to do something what I think to be fairly cool. Let's add this term to both sides of the equation, right? Let's take this and let's put it onto this side of the equation. Well, if I take this and put it on this side of the equation, what happens? I then have two of these on the left side of the equation. So that becomes, I mean, I could write it out. That's e to the, it's e to the x cosine of x dx plus, right? Because I'm taking this and I'm putting it on that side of the equation. E to the x cosine of x dx, right? And that's just the same thing as 2 times the integral of e to the x cosine of x dx. And then that equals this term, which equals, and I'm running out of space, e to the x cosine of x plus e to the x sine of x. I know it's really messy. But all I have to do now to solve this integral is divide both sides by 2, and I'm done. Right? So let me write it out. It's very exciting where it's the home stretch. So if I just divide both sides by 2, I get, and I'm going to try to write it so you can see everything, e to the x cosine of x dx equals, and on that side, I have e to the x cosine of x plus e to the x sine of x over 2. I think that's pretty neat. I think it's neat how integration by parts kind of allowed us to do this. We actually never even had to evaluate this integral. We said, oh, well, this integral is just the original problem again. And you can think about why that happened, right? Because these trig functions cycle. So we had to do integration by parts twice to kind of get back to where we were before. And then we use that to kind of just solve it without actually having to evaluate the integral. And what I also think is cool is that even if you just look at this solution, it's kind of neat, right? The antiderivative of e to the x. Oh, and I should never forget the plus c. That would have given me like -1 point on the exam. But what's kind of cool, the integral of e to the x cosine of x is this expression that's e to the x cosine of x plus e to the x sine of x divided by 2. It's the average. It's the average of e to the x cosine of x and e to the x sine of x. I think that's a pretty neat property, and you might want to graph them and play with them. But it's kind of neat. Hopefully, I have convinced you that this is a classic of a problem, and you also find it neat. And I'll see you in the next presentation.